Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from SK Telecom AXK1, a 519B MOE language model with controllable reasoning. This video walks through AXK1, SK Telecom's new 519 billion parameter mixture of experts language model. Even though the total parameter count is huge, only about 33 billion parameters are active for each token, which keeps inference relatively efficient. The team trained the model from scratch on roughly 10 trillion tokens, but under a strict, fixed compute and time budget. A central idea is controllable reasoning. Users can explicitly choose between a thinking mode, which produces detailed chains of thought, and a non-thinking mode, which gives concise answers. The motivation behind AXK1 comes from two pressures. First, frontier language models keep getting bigger and more expensive to train, and their strongest reasoning abilities often rely on both large parameter counts and heavy test time computation. Second, real products can't always tolerate slow, verbose chains of thought for every query. At the same time, Korea wants a high-end foundation model that deeply understands Korean language and culture. Without depending entirely on foreign proprietary systems, AXK1 is SK Telecom's answer to these combined challenges. The paper highlights four main contributions. First, a compute-optimal mixture of experts architecture with 519 billion total parameters, designed using MOE and vocabulary scaling laws to fit a fixed flop budget. Second, a 10 trillion token pre-training corpus built through a sophisticated pipeline with document parsing, synthetic data generation, and classifier-based curation. Third, a ThinkFusion post-training recipe that fuses a reasoning-heavy model and an instruction-following model into a single checkpoint with explicit mode control. And finally, extensive evaluations showing that AXK1 is competitive with leading open-weight models, with particular strength in Korean tasks and mathematical reasoning. Let's look at the architecture. AXK1 is a large mixture of experts transformer with 519 billion total parameters, but only about 33 billion are active for each token, thanks to sparse expert routing. The model has 61 layers and 64 attention heads, and it uses multi-head latent attention, or MLA, to make key-value caching and long-context inference more memory efficient. The MOE blocks combine routed experts with a shared expert, following recent large-scale MOE designs. The model size wasn't chosen arbitrarily. The team started from a fixed training window of about 75 days on a cluster of H200 GPUs, and estimated a total compute budget of roughly 2.5 times 10 to the 24 flops. They then applied a mixture of expert scaling law that maps available compute to an optimal total parameter count, which landed near 5.19 times 10 to the 11 parameters, or 519 billion. They also tuned the expert granularity, the ratio between model width and expert capacity, to favor stability and efficiency under realistic, imperfect expert routing, rather than assuming ideal load balancing. Large MOE models can be fragile during early training. To stabilize optimization, AXK1 uses a dual normalization scheme. RMS norm is applied both before and after the MLP and MOE layers. This design is inspired by Gemma-style architectures and helps suppress loss spikes that appeared in early dry-run experiments. Compared to some GLM variants that stack multiple norms around the MLP, AXK1's setup is slightly simpler while still delivering smoother training curves. Tokenization is a major design lever, especially for multilingual and code-heavy workloads. AXK1 uses a byte-level BPE tokenizer with a relatively large 160,000 token vocabulary. This size was guided by a vocabulary scaling law, which suggested around 132,000 tokens for the architecture, then adjusted upward based on experiments in a 10 trillion token training regime. The tokenizer is trained on multiple languages, including English, Korean, Chinese, Japanese, and Spanish. The vocabulary size is also chosen as a multiple of 128 to align well with GPU tensor cores, improving embedding and projection efficiency. How well does this tokenizer actually compress text? The authors compare average tokens per sample against OpenAI's O200K and Qwen 3 tokenizers. AXK1's tokenizer uses substantially fewer tokens for Korean general text, reasoning text, and math, which is crucial for Korean-centric applications. For English and code, its efficiency is competitive with strong baselines. For other languages like Chinese, Japanese, and Spanish, the picture is mixed, reflecting the trade-offs of optimizing for Korean and broad multilingual coverage at the same time. The pre-training data pipeline is a major part of the story. the team assembled a 10 trillion token corpus from diverse sources: web pages, code, books, academic literature, Q&A sites, STEM content, and explicit reasoning data. They built an in-house document parsing pipeline using a vision language model to extract structured text from complex PDFs, including multi-column layouts and tables. On top of that, they generated synthetic data to deepen reasoning signals and fill topic gaps. All of this flows through a multi-stage curation pipeline that handles cleaning, anonymization, deduplication, and classifier-based filtering by quality, domain, and difficulty. The data mixture is not static. In Stage 1, the model sees mostly web data plus some code, encyclopedias, and Q&A to build broad linguistic and world knowledge. In Stage 2, the mix shifts toward code, mathematics, STEM, and explicit reasoning, while web share decreases. By Stage 3, long context training, math, STEM, and reasoning categories are heavily upsampled, and web is further reduced. This progression acts like a curriculum, moving from broad, easier content to more specialized and difficult material as training proceeds. Pre-training is organized into 3 conceptual stages. First, a general knowledge stage, 7 trillion tokens at a 4,000 token context length, with a constant learning rate to maximize knowledge absorption. Second, a high-quality reasoning stage, about 1.66 trillion tokens of carefully filtered, complex web data, STEM, reasoning tasks, refined PDFs, and synthetic data, with a decaying learning rate to stabilize on this higher quality distribution. Third, a long context adaptation stage, 600 billion tokens used to gradually extend the context from 4,000 to 16,000 and then 32,000 tokens, with learning rate decay during the mid-extension and a flat rate at the final length. The optimization setup is tightly coupled to the scaling laws. The peak learning rate and global batch size are computed from the same MOE scaling law that set the model size, then slightly adjusted for throughput. They use AtomW with standard momentum settings, keeping parameters and gradients in FP32 while optimizer statistics live in BF16. Most activations and eligible tensors are stored in FP8, with E4M3 for the forward pass and E5M2 for the backward pass. On the parallelism side, they use pipeline parallelism of 16 and expert parallelism of 8, without tensor parallelism because H200 memory is large enough. For long contexts, they add context parallelism, splitting attention across devices at 16K and 32K sequence lengths. In practice, theoretical flop budgets don't automatically translate into real throughput. The team profiled their system and found that a baseline configuration with expert parallelism 32 and pipeline parallelism 8 only delivered about 95 teraflops per GPU. By reconfiguring to expert parallelism 8 and pipeline parallelism 16, they more than doubled throughput. Introducing FP8 training and a fused cross-entropy kernel added further gains, reaching around 302 teraflops per GPU. To stay on schedule and preserve the intended total compute, they also expanded the cluster from 1,024 to 1,536 H200 GPUs. Managing memory is critical for a 519 billion parameter MOE model. Instead of recomputing every activation, which would significantly slow training, the authors selectively apply activation recomputation to the most memory-hungry parts: the up-projection and multi-head latent attention, and the MLP layers. This targeted strategy reduces peak memory enough to fit both 4K and long context runs on H200 GPUs, without paying the large throughput penalty of full recomputation. After pre-training, A.X K1 goes through a 3-stage post-training pipeline. First, they fine-tune 2 separate models, one for instruction following without explicit thoughts, and one for reasoning with explicit chains of thought. Second, they fuse these models into a single checkpoint and run an additional supervised fine-tuning step to align the 2 behaviors. Third, they apply on-policy reinforcement learning to sharpen instruction following and enforce correct use of the thinking tags. The end result is a single model that can reliably switch between thinking and non-thinking modes on demand. In the first post-training stage, the team trains 2 distinct models, starting from the same pre-trained checkpoint. The Instruct SFT model is trained on standard instruction following data, summarization, rewriting, retrieval-style QA, tool use, without any explicit reasoning tags. The Reasoning SFT model is trained on math, code, STEM, tool use, and agentic trajectories that include explicit chains of thought wrapped in think tags. English data largely come from open-source repositories, while Korean data are curated and augmented in-house. This yields two specialized models, one that's concise and one that's deeply reasoning-oriented. The second stage, Think Fusion, starts by linearly merging the two SFT models. The fused parameters are a weighted average, alpha times the reasoning model, plus 1 minus alpha times the instruction model. In practice, they set alpha to about 0.8, intentionally biasing the merged model towards strong reasoning. However, naive merging isn't enough. It tends to blur the distinction between modes, leading to over-verbose answers in non-thinking mode and malformed or inconsistent think tags. That's why the authors add a dedicated fine-tuning step on a carefully constructed dataset. To fix mode confusion, the authors build a mode overlap dataset. For each prompt, they include two target responses, one with a full chain of thought in thinking mode and one concise answer in non-thinking mode. The fused model is then fine-tuned on this mixed distribution, minimizing standard language modeling loss. This teaches the model that the same instruction can legitimately lead to two different styles of output, depending on the control tokens. As a result, the model maintains strong reasoning ability when asked to think, but can still produce short, direct answers when thinking is disabled. The final post-training stage uses on-policy reinforcement learning. For each base instruction, they create two prompt variants, one that appends a think token to trigger reasoning, and one that appends a closing think to request a direct answer. These are treated as separate training samples. The optimization uses a GSPO-style sequence-level loss within the DAPO framework, which is more stable for MOE models than token-level objectives. Rewards have two parts, a correctness term that rewards right answers and penalizes wrong ones, and a format term that penalizes incorrect or ambiguous use of the thinking tags. This enforces both good content and clean controllability. To evaluate A.X K1, the authors use a broad suite of benchmarks grouped into 7 categories: mathematics, code, general knowledge, Korean-specific tasks, instruction following, long context understanding, and agent performance. They combine widely used public benchmarks with in-house Korean datasets to better reflect local usage. Thinking mode is tested with prompts that explicitly encourage or require chain-of-thought reasoning, while non-thinking mode is tested with prompts that ask for direct, concise answers. In thinking mode, A.X K1 performs very well relative to other large open-weight models like DeepSeek v3.1 and GLM 4.6. On the AIM-25 math benchmark, it achieves about 89.8%, slightly ahead of both baselines. On KMMLU, a Korean counterpart to MMLU, it scores around 80.2%, showing strong understanding of Korean academic and professional content. For code, it is competitive on live code bench and human evil style tasks, including Korean variants. The main weaknesses appear on the most demanding long context and advanced knowledge benchmarks, where models trained with larger compute budgets still have an edge. In non-thinking mode, the picture is more mixed. A.X K1 achieves the highest score on IF Bench, which stresses instruction following under looser prompting conditions. However, it lags behind DeepSeek v3.1 and GLM 4.6 on IF Evil and on several Korean knowledge benchmarks when chains of thought are not used. It also underperforms on code benchmarks in non-thinking mode. These results reflect both the limited training compute compared to the baselines and the deliberate emphasis on strengthening reasoning behavior in thinking mode. This slide highlights the detailed benchmark comparison for thinking mode. You can see how A.X K1 stacks up against DeepSeek v3.1 and GLM 4.6 across Korean knowledge, English knowledge, instruction following, math, code, long context, and agent tasks. The pattern is clear. A.X K1 is especially strong in Korean and math, competitive in code, and somewhat behind on the most demanding long context and advanced English knowledge benchmarks. The authors are explicit about limitations. Expert parallelism is capped at 8 because their networking stack didn't scale efficiently beyond that, even though the algorithm could in principle. Their overall compute and time budget is smaller than what some frontier models enjoy, which likely contributes to the performance gap on the hardest benchmarks. A.X K1 is also text-only for now, without built-in multimodal understanding. Finally, while thinking mode is strong, non-thinking performance, especially on code and some knowledge tasks, still has room to grow. Stepping back, A.X K1 shows that it's possible to build a frontier-scale mixture of experts model under real-world constraints by carefully following scaling laws and aggressively optimizing systems. It also demonstrates that explicit control over reasoning, switching between thinking and non-thinking modes, is practical even at the 500 billion parameter scale. Looking ahead, the team plans to add native multimodal capabilities and continue scaling toward the trillion parameter regime, while leveraging the engineering lessons from this project. At the same time, AXK1 serves as a key building block for Korea's broader sovereign AI ecosystem.